here to speak about my research topic, which is Model for an Artificially Intelligent Operating System built on decentralized and distributed infrastructure. In this presentation, I'm going to discuss the related research about our hypothesis. I'm going to go talk through our hypothesis as well as the empirical evidence I found during my experimentation, as well as conclusions and room for improvement in the future. So as an introduction, the goal of this project is to bridge the gap between two of the most technologically advanced and sophisticated fields in computer science at the moment, which is AI, artificial intelligence, and blockchain technology, which is related to cryptocurrencies and distributed ledgers. Together, AI and blockchain can be used together to create decentralized and autonomous systems that aim to be unbiased, truthful, and fair. In our hypothesized model, we aim to show that a feasible model exists for a artificial intelligent operating system built on decentralized and distributed infrastructure. Essentially, we're going to talk about topics such as distributed information processing, machine learning, system design, as well as blockchain technology. So there has been some related research as part of forming our hypothesis. The first one is related to an intelligent operating system which runs a particular machine learning model which is used in computer vision. That paper was a motivating example for our experiment. The second one is autonomous decentralized software structure in this application. This relates to blockchain technology and DAOs, which are decentralized autonomous organizations. And the last paper is Decentralizing Collaborative AI on Blockchain, which was published by Microsoft Research. Some of the motivating examples for forming this hypothesis of mine was two very interesting topics and leaders in their respective fields. On the cryptocurrency and blockchain side of things, the Ethereum virtual machine is an operating system of its own, which allows holders of the Ethereum token to run smart contracts, and is built upon a proof of stake consensus algorithm, which means that all the transactions are validated and approved by the network. The second is IBM Watson, which is an artificial intelligence system. This takes into its own hands business applications that use AI, task automation, as well as predicting future outcomes. It is being used by a large amount of businesses at the moment and currently has an incredibly high computational overhead of near $1 billion of research and development. Computational overhead is something that we'll discuss later on towards the end of the presentation, as it is very computationally expensive to run such models at scale. So for our hypothesis, we were able to draw up a system diagram for the interactions between different components and processes that are running concurrently in the system. As you can see, we have a central operating system which manages assets, applies ML models, and communicates with a validation engine, which allows for the system to be intelligent, secure, and truthful, as well as transparent at all levels. And because we're using asymmetric encryption, we're able to maintain secure access to our files as well as security across the network. I talked about the network. I would like to give more insight into network structure. Essentially, the previous image shows what any single client node in the network has. They have the ability to function as a validation engine or communicate with one, speak and communicate with the distributed ledger of models, as well as manage decentralized applications, as well as the user client node's assets. As you can see, the client node is participating in the network, and it communicates with the validation nodes to ensure that all the information that they're seeing as part of any functions that they're running, any kind of applications running on that specific network, is validated. So in this case, we aim to use n validation nodes in our network. In our hypothesis case, we use 6, and we allow them to individually communicate with the client node as well as neighboring validation nodes. The client node sends out a request, and the validation nodes fulfill the request by ensuring that the output of the model is accurate by majority vote, which is used as part of our consensus algorithm. Key issues that we want to address by building such a system. First is scalability. We want our operating system to be scalable and allow for validation nodes to cover specified regions and availability zones on the distributed network. This ensures that there is enough room for client nodes to participate, but luckily, as I mentioned, a client node can also participate as a validation node. It's all built into the system, which makes it really easy and uniform across all nodes. Secondly, we're going to talk about availability. Availability, you want to ensure that there is at least one node at all times with a complete copy of the distributed ledger. This is to ensure that there is no downtime in the network. Essentially, for such a system to run at scale, you would need a lot of validation nodes running concurrently in different regions and availability zones. And lastly, we want to talk about security. In this case, we want to use AES 256 asymmetric encryption schema, which uses a public and private key to access information and participate in the network securely. This is used and given to a client node as stored in their operating system. Now we can talk about our empirical evidence. On the right, you can see two charts. The first chart is the hypothesis target variables that we aim for our experiment ML model that we are going to use. Using supervised learning and convolutional neural networks to classify objects as recyclable or non-recyclable. This is a classification problem. For training, the target value is 0 or 1, corresponding to a recyclable or non-recyclable object, so it is binary classification in this case, and we will use a validation which tests the accuracy to ensure that it reaches the target value based on the accuracy of the training. Next in our chart, you can see the ML model accuracy. You can see that we selected 4 common ML algorithms that are using computer vision to detect whether an object is recyclable or non-recyclable. In this case, because of the computational overhead of running such a system, we had to draw up arbitrary values just to see how these values will participate in a network. Next, we'd like to propose some pseudocode for how the system behavior will run when validating and checking which model is the accepted model as part of the distributed ledger. At first, you can set a model accuracy of 0 and there is no chosen models, and you can have all models stored in an array, and in the array you can test and see which of the ML models is the accepted and chosen models. This is something you can validate anytime during the network, and that is what's checked. While the framework is true, you can iterate through all the models and see if the accuracy of a specific model is greater than the current accepted model accuracy. If so, the chosen model is the new model, and you can increment and push a web service onto the chosen model. To conclude, the hypothesis artificial intelligent operating system model is theoretically feasible. The application infrastructure of the operating system, the network infrastructure for the client and validation node supports our hypothesis of available, scalable, and secure distributed system that is fair, transparent, and unbiased. I know I threw a lot at you guys, and I hope you guys were able to pay attention. But in our future work, we hope to test our hypothesis and machine learning models on a production server with a client node as well as end validation nodes to see how practical and computationally intensive running such an infrastructure is. Thank you so much for listening, and hope you like my work. Nice talking to anyone. Feel free to reach out with any questions, comments, or concerns. That is my email. Thank you very much.